Okay, so welcome back. We're doing lesson 4, still review from grade 11. At this moment, if you feel like you're really falling behind, my biggest suggestion is please send me a message, right? Let's see what I can help you with. Um, the other things are I did post textbook, right? It's a good idea to read into the textbook if you feel like you needed other stuff, just to get caught up with. Okay, so this is lesson 4. So, relative relative motion. So we're still dealing with vectors, but this time we have been dealing with vector, but mainly we've been talking about displacement. But vectors can be applied to forces. Vector can be applied to velocity. So today the main thing that we're going to talk about in terms of vectors are velocity. Oops, it's spelled velocity, right? Okay, let's see. Let's do this again. So velocity is going to be what we're covering. And basically because velocity is a vector, we can still use vector diagrams. But in the same diagram, make sure that velocity is all that you're using. You're not going to put different like two vectors that are velocity, but you can't add it to a displacement because they're not measuring the same thing. And what it means by relative motion is, say for example, right now you feel like you're sitting at rest, right? Like I'm sitting on my chair, I'm not moving. But one thing that you can think of, it's almost like you, if somebody else is stepping outside of the world looking at you, you're actually not stationary. You're actually moving at a very fast speed because the earth is spinning. Okay, same thing with these airplane pictures. The airplane looks really fast. Like say if you go to an air show with I I was gonna say Canadian Tires. What do I want to CNE? You know that exhibition thingy like every August. I don't think we have the air show anymore. We would always take our kids down and we would put like the little earmuff thingy for them, and then they would wear it, and we would go and watch. The, Obviously the plane are going really fast, but when they're doing a formation relative to each other, they almost look stationary, and that's what relative motion is talking about. Okay, so it's important to talk about the frame of references, and a lot of time we reference to the earth. Okay, so that's why you're saying, oh, you're not moving, or if I'm standing, if I'm in the classroom looking at you, you're like, oh, we're stationary in comparison to each other. But it all depends on where you're looking at, and this is where this humongously complicated um, vector for say a plane. Commonly used languages, if it's velocity, if I'm talking about this first guy, okay, so I'm reading out this guy right now. um, this is called the velocity of the plane relative to the earth. This is what I need you to write out. Okay, please write it in your note. Commonly used wordings for the first term, we call this the ground speed. What ground speed means, if I have a guy who is looking at this airplane, this is an airplane. Oh no, shouldn't have the I there. Let's do it again. So if I'm looking at this airplane, really what it looks, how fast it's going, because the pilot could be pointing it whatever direction. We call it the airspeed. Okay, so let's go to this. Velocity of the plane relative to the air. If you're flying, if you are in the air right now and you're just drifting along the air, you basically would only see what the pilot is gearing the plane, right? We call this the airspeed. So if you're drifting in the air with the airplane, you would notice this velocity of the plane relative to the air. So basically, what the engine is doing, how fast the engine is pushing, and how fast the pilot thinks he's flying. But then don't forget, there are going to be, tornado. I don't know if you heard. There's probably going to be another hurricane from the state in the states, which is gonna is stewing up right now. But this is the wind speed. We call this the wind speed because at the same time the airplane is flying, don't forget we're gonna have these winds that are pushing it off course, and so when the guy on the ground looking at it, the plane, whatever the headings of the pilot is going, it's going to be affected by the wind that is blowing it off course. Okay, and those are what the prefixes. I don't need you to know this VPE, VPA, VAE stuff, but I do need you to know ground speed versus airspeed versus wind speed and how they would affect it. Okay, Let's do a plain question. I like plain question. Let's do example number 3 first. Okay, this is the bad wording. If you don't mind, can you just change this up? I don't like the 400. Can you add the 400.0 kilometers per hour north 25 east? I just wanted it to be, not one sig. Same thing. This is 80.0. Okay, so it's telling you that this pilot, I'm on number 3 right now. We'll go back to the other ones later on. Okay, a pilot wants to fly at 400 kilometers per hour north 25 east when you have a wind that is blowing at 80 kilometers per hour south 25 east. Okay, so the 400 is the airspeed, and they want you to calculate the ground speed. Okay, so what is this doing? You would draw the picture almost exactly the same as what you would do with a displacement question. Remember the resultant displacement question that we were working on in terms of the vectors? So you would start off with like a starting point. So north 25 east, you have extra space you could use. I would totally suggest you take a look, draw it bigger, because these questions has lots of angles and stuff like that. Okay, so north 25 east. So I'm going to do my little crosshair here. North 25 east, meaning from north, I'm swinging towards the east direction. So this angle right here, north 25 east. And this length of the triangle is 400. So I'm going to say 400 kilometers per hour. And that's the first one. And then the wind is blowing it to south 25 east. So as always drawing vector diagram, we keep going. I don't go back to the starting point, right? I would keep going. Now the wind pushing it south 25 east, meaning from the south, it's swinging towards the east direction. This is 80, so it's a shorter vector. Even though I don't draw it to scale, I still make it relatively close, just so that it gives me a better idea, right? So I have north 25 east and then south 25 east, and the length of this vector is 80 kilometers per hour. And just like before, to complete the picture, to get the ground speed, basically you go from starting point to ending point. So I started here, and I'm going to draw my resultant vector. I just like to call it VR. You can call it VPG, velocity of the plane relative to the ground, if you want. You can call it X if you want. It doesn't matter. The key thing to check, did you have angles and stuff? Like, did you include the direction? Like, I'm going to highlight it. I'll erase it after. Do you have arrows along your pictures, right? These are vector pictures. If you don't put your arrows, you're going to lose communication mark, right? So I'm going to undo this. All right. So this is what I have. And now this is not a right angle triangle. What that means is I'm going to have to use either sine law or cosine law. Right? I cannot use SOHCAHTOA because it's not a right angle triangle. So in order to actually use cosine law and sine law, we actually need a complete angles inside the triangle, because right now I have the 25 that's at the bottom here, but it's outside of the triangle, and then I have this 25 here, but it's not really in one of the angle inside the triangle. So we need to somehow do something to figure out what are the angles that are inside the triangle. There are many different ways that you can look at it, and I'm going to show you a couple of different ways. I'm going to be scribbling all over this page, and then I'll clean it up before we actually move into the map. Okay, so the red 25 that's up here, it's already inside, sort of inside the triangle, so which is a good thing. But this 25 black one outside is outside the triangle. So how do I move it inside? It depends. If you were, I don't know if you remember any of these, you can use the parallel line theorem, the Z pattern, or you can use the angle sum of triangle theorem, and any of it, or the complementary angle theorem. These are all from, like, I don't know, geometry when you were in grade 9, maybe? I don't remember. Whatever way works for you. Okay, so I'm going to go through the first one, the parallel lines theorem. Okay, I need to find parallel lines, and I'm going to draw in the parallel line. North and south, and north and south parallel to each other. Do you see that? And then there is a black line which is where the 400, there is a line here. Okay, super messy, I know. Okay, I need to find the parallel line theorem. Do you see the bottom 25? I can bring it to the top because I'm going to use this blue highlighter, okay? The Z pattern. Do you see the Z pattern? This angle is also 25, which is the same as this. This is your Z pattern. That's the first way that you can get it. So north and south are parallel. I find the Z pattern. Okay, I'm going to do this. I'm going to do this. Another way that you could do, I'm going to use black pen. This is 90. That means this angle has to be 90 minus 25 because that's a complementary angle theorem. Any right angle adds to 90. So this is 65. You okay with that? 65, if I complete this triangle, do you see this is a right angle? If I have a right angle of 90 and I have a 65, angle sum of triangle theorem all adds to 180. So 180 minus 65 minus 90, 25 degrees again. Okay, so different ways you can look at it. I'm going to clean this up because we're now going to move on to the cosine law and all those stuff. So I'm going to clean all of these up. You can pause the video, copy it out from before if you want. I'm just going to make this really clean. So I have gotten that this angle is also 25, meaning together, I'm going to change the color, meaning together this angle is 25 plus 25, so 50. And now take a look at my triangle. I have a triangle here. I know 400, I know 80, I know the angle in between it. I'm going to use the cosine law. Okay, so the cosine law is VR squared. It's 400 squared plus 80 squared minus 2 times 400 times 80 cosine of 50. Learn how to punch it in your calculator. I usually just punch all of them in the calculator. A lot of people make mistake and they started making an equal sign here before they multiply by 50. What you've done is you've multiplied everybody by the cosine of 50. So don't do that, right? So literally I would punch it straight into the calculator. So 400 square times 80 square minus 2 times 400 times 80 times cosine of 50 equal. Okay, VR squared equals to this whole thing. So that means I need to take the root of the VR. So I'm going to take the square root equal. Okay, so I got like on my calculator, I got something like 353.923, so on and so forth. The unit is still kilometers per hour, right? So number one, watch for your sig digs. I did want it. So there's 4 sig digs in 400.0 and 3 sig digs on 80.0. So I'm going to keep 3 sig digs. So I'm just going to round it off with 3 sig digs. So these are the 3 I'm keeping. I'm rounding this. So because the 9 is greater than 5, I'm going to round up to 354 kilometers per hour. This is 3 marks out of 5 right now. You got a picture? That's 1 mark. Okay, and then you got 1 mark for showing me the work, 1 mark for getting the answer. But don't forget, this is a vector question. So that means you still need to figure out your directions. So that means you need to find the angle using the sine law. And to do that, we right now have a triangle. We now know that this VR is equals to 354. So I have 50 and the side opposite to it, right? So when I have that, I can use my sine law. Do you see how when I have a side and an angle opposite to it, so this is the pair that I do know, I can use the sine law. And you always find the tail of the resultant. So this light green pencil, the tail of it, that means I need to find, with the light green, I need to find from north, how far is it swinging towards the green line. And to do that, I'm going to have to make use of the triangle. I'm going to have to calculate what is angle theta inside the triangle, and I need to add it to the 25. Right? So what that means is I'm going to have to find out what is 25 plus whatever theta is worked out to be. That's going to be the direction that I'm going to write down. The general direction, it's a northeast, right? So north, I'm swinging north, going towards the east direction. So I'm going to have north, something, something, east. So I'm going to have to figure out what is angle theta. All right, if the triangle looks messy, just redraw it, right? So I know I have lots of stuff, so I'm just going to redraw it. I got a triangle. This is 80. This is 400. I know this is 50. I know this is 354. I would like to find this angle. Okay, so sine of angle theta divided by 80 is going to equal to sine of angle 50 opposite to the 354. Okay, so when I have sine law, I do the cross multiplying. I'm going to change the color. You don't have to write it down. Honestly, you can literally punch it in the calculator and just tell me what is angle theta. Just punch it in, but I'm just going to show the steps just to make sure people are on board. I'm going to change it to this light color. So I need to cross multiply, meaning 354 times the sine of theta is equals to 80 times the sine of 50. To get sine theta on its own, I'm going to have to divide both sides by the 354. So sine theta equals to 80 sine of 50 degree divided by 354. And to get angle theta, you go second sine. So I'm going to punch it in the calculator. So 80 times sine of 50 divided by, so I know I talked about this before, you can just divide it by 3 by 4. You punch it in. Or 350, like this whole gibberish big number is actually in the ANS, the store answer button on it. So I'm going to actually say divided by the answer that I got so that I have all the decimal places that are there. I'm going to press equal, and then I'm going to go shift sign to get the inverse of the sine, and I got the angle to be 9.97, so the angle is 10. So that means if I now finish off the question, the actual angle is 25 plus 10, which equals to 35 degrees. A canoe can paddle at a speed of 2.2 meters per second in still water. Then you got, so this is almost like what we were talking about, like almost like the airspeed. So when there is no water, this is how strong the pedal is. Then there's a river at 1.4 meters per second flowing towards the west direction. The canoe is aiming north. The river is 120 meters wide. Okay, so just imagine the northeast southwest. Canoe is going west. The river current is going to the west direction. Okay, so let's just draw some picture. So I know that the river kind of goes this way, right? And they tell you the width of the river, it's 120 meters. Key thing in mind, they're giving us different values, some in meters and some in velocity. So make sure we don't mix it up. And they tell you that you got this canoe that is paddling going north, and it's telling you that you got this river current. I'm just going to change the color again. So I got this river that is flowing at 1.4 meters per second west. Okay, so let's see what I can do to complete the triangle. At still water, so if the canoe is just going north in still water, it is going at 2.2 meters per second. And while it's going straight up that way, because the current is flowing at 1.4, it's gonna, does that make sense that it doesn't go all the way straight north and then go. It's actually a continuous motion that as I'm going up north, the river is pushing me towards the west direction. Does that make sense? Okay, but in terms of vector sum, when we're drawing pictures, one easy way to do is we know that if the river is pushing, ultimately at the end, my boat, which is like a ground speed, if somebody is standing on the ground looking at how the boat is going, the boat will look like it's traveling this direction. I have people who, I don't know if you just signed in and out. Is there anybody who hasn't signed in through the Google form? Because I already sent in the attendance. Type in the chat if I need to resend the assignment. Corey, negative 1, 2, 3. I think it's 3. It has to move behind the. Where's your 8? Is it 0.008374? Is that the question? Okay, then you should move it behind the 8, not the 3. You always move it behind the first number that is not a 0. So 8 is your first number that is not a 0, right? Yes. You do keep all the decimals that are there, but you put the decimal place in the right spot. 374. So you need to figure out how many times, where it needs to go. My old decimal place is here, but my new decimal place goes behind the first number that is not a 0. So meaning right here, I need my new guy to be here. So I need to figure out how many times I need to move it. So 1, 2, 3. Do you see how I move it 3 spots? Okay, so my new number becomes 8.374 times 10. How many times? 3 times, because I moved towards the right. It's a negative 3. Okay, so question A asks, what is the speed? So I need to find out what is the speed of the canoe relative to the shore. So that means this purple one standing on the ground, looking at basically finding the length of the purple. And so, because this is a right angle, do you see how I go from north to west? This is a right angle triangle, so I am allowed to use SOHCAHTOA. Right? So I'm finding the hypotenuse. So 2.2 square adding 1.4 square is going to equal to, okay, I didn't label it properly. I'm going to call this VR. We're still talking about velocity, so the resultant velocity. So I'm using the hypotenuse, the Pythagorean theorem. Punch it in, 2.2 square plus 1.4 square. Take the square root. So my VR work out to be 2.6. I keep 2 significant digits. I'm going to round it to 2.6. The unit is meters per second, and I hope you know you're not done because you need the corrections. These are vector. Look at the triangle. I will always do the tail of the resultant. So the purple line, the resultant velocity, I always do the tail. So I need to find the angle that is at the bottom of the triangle. And so I have opposite and I have adjacent. You actually could use your hypotenuse too. I always tend to pick numbers that are already given to me in the question, so I don't have to worry about rounding. It's more accurate. So I have opposite and adjacent. I'm going to use the TOA. So tangent of angle theta is opposite, which is the 1.4, over the adjacent, which is 2.2. Work that out. So 1.4 divided by 2.2 equals, to get the angle theta, I have to go shift tangent, and it worked out to be 32 degrees. So angle theta is 32 degrees. And so to put it in a direction, the purple line is swinging north, going to 32 degrees to the west direction. Okay, how long it takes to cross the river. This is the tricky one. You need to match the side of the triangle, because when I'm talking about time, we're assuming these are constant velocity question. I'm using the constant velocity equation. So velocity is displacement over time. I know I need some sort of velocity and I need some sort of distance for me to figure out what is the time. You basically would have to match the side of the triangle together. So I have a distance or a displacement that is 120. Do you see how it's going up and down? You would have to match it with the velocity that is going at the same time. Okay, so velocity is 2.2 equals to displacement, which is 120, over the time. Okay, And then to figure this out, don't forget my delta t is at the bottom, so you can swap it. The easiest way to do, it's almost like you do a cross multiplying. Delta t is 120 over 2.2. And the time it worked out to be is 55 seconds. Okay, so when they ask how long it takes, we're looking for the time. Oh, we did the time. And I need you to keep in mind that the time it takes to go across the river, it's the same time that it takes for you to go over by the river. And means if Billy is looking at you, that's also the amount of time he looks at this. So keep in mind for all three sides, your time is the same. Okay, so you might want to make a little note in here. The time are the same for all three sides. Because when it comes down to how far downstream the river will the canoe end up, I need to know this guy. If I'm looking for the displacement for this guy, I know that the time is still the 55. So I would use the time at the 55 seconds. I would use the velocity at the 1.4. And then use the same equation. Velocity is displacement over time. 1.4 equals delta d over the time, which is 55. You rearrange the equation, multiply the 55 on the other side, times 1.4. So I got something like an 81.8. See, I don't round. I always use the answer button, but I'm going to keep two significant digits. So it worked out to be 82 meters, and the direction is west. So last question. The same canoe from problem 1 now wants to arrive directly north across the river. In what direction must the canoe be aimed and what speed relative to the shore? So my river is still going to be the same width, right? 120. And the current is still flowing towards the west direction at 1.4. If the canoe head directly straight north, it's going to be pushed towards the west direction from the river, right? So to counter that, he's going to head a bit more to the east. So the canoe is going to have to point this way to the east so that the river will push them towards the west so that you will end up directly across the river. Okay, so where does 1.4 go? Okay, I think 1.4 is the current, so it's pretty straightforward that the 1.4 meters per second is here. The only thing I do not know is where does the 2.2, okay, where does the 2.2 go? So 2.2 is the velocity of the canoe when there is no current, right? In still water, it is going at 2.2. So what do you think, which side of the triangle would the 2.2 have to go if there is no current? Okay, so if there is no 1.4, does it make sense that the 2.2 should go here? Because if there's no current pushing, he will end up not directly north, but somewhere towards the east direction, because that's what you're hitting. Okay, finally they want you to find what directions you want to aim. So you are looking for this angle. And it is no longer tangent. Be careful. Your 2.2 is now your hypotenuse. So this is my hypotenuse and this is my opposite. This is a right angle triangle. So I am going to have to use sine. So sine of angle theta is equals to opposite, which is 1.4, divided by the hypotenuse, which is 2.2. Plug in your calculator. So 1.4 divided by 2.2 equal, and then to get the angle, shift sine of an angle, which is 39.5, so 40. Okay, I don't know if I ever mentioned for angle, don't worry about sig digs. Can you read what I'm writing? Don't worry about sig digs, okay? Just because when it goes to sine and cosine and tangent, they have a completely new rules of how to name, to count the significant digits and stuff. So we're not going to get into it. We're just always going to round to the nearest angle. Okay, so that's 40. So meaning the direction that he's going to have to head is going to be north 40 degrees towards the east direction, so that it's going to counter the current that's moving to the west, pushing it directly north. Last question. What is the speed of the canoe relative to the shore? So they would like you to find out what is now the new VR. It is still called VR because it is still the resultant by this guy watching on the river, and it will see that it's going north. Okay, so right angle triangle, but this time your hypotenuse is 2.2. So 2.2 square equals VR square adding 1.4 square. So 2.2 square minus 1.4 square equal, take the square root, 1.69. So 1.7 meters per second, and the direction is north.